Right. Okay. Right. So before we start, let's check the EduNext, and then let me tell you what is inside. So I think I will put the, okay. Can you see my screens now? Okay, right. Okay, everyone, can you hear me? You may want to open your cameras.
Yes, yes.
Okay, right. Okay, so now we're in week 9. Okay, and I'm gonna add here that week 10 is the I'm gonna add here is the module 2 exam. Okay, so we have 3 module there. Okay, right. So for uh, what is included in the module 2 exam is actually starts from here, from the module 6 or the week 6, about the statistical inference for single samples. Yeah, you have the learning videos. I also put the recording. Yeah, also put the recording at the back there. So even you can also access it on MS Team, but I'll also put the recording here. Okay, just for the convenience. And then you have the learning video, you have the learning video in Bahasa Indonesia. Okay, and then this is module 7. Okay, this one is module 7, is the statistical inference for testing here. And then you have this one is all, and we also have the course recording. Yeah, we also have the course recording for the week 7. Okay, and then the next one is the module 8, which is last week. Module in EduNext means week. Yeah, so if you access the module 8, for example, so you access the handouts and also the presentation and also the videos for week 8. Okay, and then this is for the module 8, and then also you have the recording, and now is the regression. Okay, so what I'm gonna explain today is the PPT on the simple linear regression. There are 3 PowerPoints, or in here is in PDF. The second one is the quality of regression, and then also how to do the regression with care. Okay, so I'm gonna explain in a minute. And also here we have the learning video from Bu Helen, yeah, from last week's learning video. There are 3 as well. And also there's also tutorial regression, but the tutorial is in Indonesia because it is made with Pamiki. Okay, so yeah, this one is the tutorial. Okay, so there's quite a lot of handout and also learning videos, and quite a lot of things to learn in 1 week. So I would suggest you to maybe have a increment those times. Yeah, have a maybe 25 minutes rule to read, to watch again, to replay again, and then try to do it by yourself in your books, so it make you easier to do the exam. Right. Okay, so I'm gonna close the session here. Right. Okay. Okay, so far any questions? No? All right. Okay, good. You are feel free to open the book if you want. Yeah, like of your friends. Okay, but I want to check the books. Okay, feel free to read the book. I do love reading the book because I can I can have a like communication interaction with the public with the authors, yeah, how they want to watch or how they want to explain something. But if you don't have time for that, if you watch the PowerPoint, read the PowerPoint, or if you also watch the video and then maybe pause and replay and try to do it by yourself, I'm sure you can understand as well. Okay, so I'm gonna start put the tutorial, the lecture for regression. So what is regression? Okay, so I'm just gonna check how many of you now. Okay, so there are 28, so around 26 or 27 with me. Okay, only 26. So where are the other 5? Right. Okay. Okay, so I have 3 windows here. I have 3 windows here, the simple linear and also, okay. Okay. So let me, okay, you can still see my full screen videos, right? Okay. All right. Now you can close your cameras because in MS Team I can't see you. But if you have a questions, please just open your microphone and ask me, okay? Or if I want to have a question to you, if I ask something to you, please answer using open the microphone. Okay? Can you hear me?
Yes, Miss.
Okay, right. Okay, so today we're going to talk about linear regression. So what is linear regression? In chemical engineering or in many engineering field or in every or maybe in our daily activities, there are so chemical engineering utilize many mathematical models. Okay, it is very important because we want to understand the behavior of the system. So if we can understand the behavior of the system, it can be controlled. For example, you also learn, I think, the mathematical analysis, yeah, or analysis matematika teknik kimia, the matek. You want to understand the behavior of the tank, for example, the for example the correlation between the input valve or the input flow and also the output flow, for example, okay, or maybe for example in let me check, or maybe in your kimia dasar praktikum, yeah, or in your chemistry practicum, in your chemistry lab, you want to find the correlation or you want to do the calibration, okay, and then we usually use that with linear regression. And then so once we know the behavior of the system, we can also control. Is it increasing? Is it decreasing? Is it, for example, we have, is it quadratic, for example, and then we have optimum result or something like that, okay? So, so there are 2 types of models. The first one is the mechanistic model. The mechanistic model is the models that we know the mechanism or the physics inside it. Uh, for example, F equal to M multiply with A, yeah, for example, yeah, force equal to mass multiply with the accelerants, or the R, for example, yeah, V divided by I, for example, sorry, R, yeah. The resistance is the voltage divided by the current, for example. Okay, so that's tell you about the mechanistic models, or in the mechanistic models, we know the mechanism of the physics in it. Okay, and usually our colleagues in physics, in mathematics, in astronomy and astrophysics, they do like to build a model based on the mechanistic model. So they check the phenomena, they evaluate the phenomena, they also see and then also investigate the phenomena, and then they try to make the model to describe the system, to describe the system, and then that's a science. Yeah, so science is they want to describe the phenomena of the system. Or the second one, so this is the first one. The second one is empirical model. We in chemical engineering do a lot of empirical model. So in empirical model, the model looks like a black box, yeah, a black box, and then we just want to know what is the behavior between the input and also the output. Okay, for example, in the chemical engineering lab tech, yeah, I ask my students to check the correlation between the flow, the Q, or the flow rate of the water coming out from the water valve with the valve opening, bukaan valve, yeah. So okay, so I ask the students to for example, to open the valve, for example, like in one opening, the second opening, and then maybe up to 2.5 opening, and then maybe they half opening as well, for example, yeah, that's a half or 1.5, for example, like that, and they put it with the bucket, and then stop it, yeah, and then for example, and then maybe measure it for example 10 seconds, and then stop it, and then they have to measure the remaining the water in the bucket from the valve, and then with the Baker glass or something, dengan gelas kimia, and then they check what is the volume. Okay, so and then the volume divided by the time, it becomes the Q, for example. So meter per second, for example, yeah, or liter per second. Okay, and then we want to know the correlation, and then the correlation maybe looks like, for example, like that, and then it become like that. Okay, like that. Okay, so that's the data. So then I would like to ask, what is the correlation, for example? Okay, so from here, so this is data, and from this data, we want to know the behavior of these models. Yeah, we want to model it. So we want to make sure what is the behavior of this correlation between the water and also the how is the flow rate? Yeah, how the flow rate of the water coming out from the valve. Okay, and then with this one. So we have to make a model. Okay, first we make the model based from the usually we want to check the model based on from our eyes. Okay, is it linear or not, or quadratic or parabolic? We look at first with our eyes. Okay, so from our eyes, is it look linear? Linear means lurus, ya, garis lurus. So it doesn't look like linear, so maybe it would be looks like that. Okay, so based on our investigation here, so we can check then. Okay, so the students can model. All right, looks like it doesn't look like linear, so I will make a model based this one. In Excel, you can make a model very easy with trend line, yeah, later on in Excel. So that's an example. So if I can make a model based on this data, so later on, if I need, for example, I want to have a Q, for example, or the volumetric rate only in this area, for example, at this point. So what I can do is just I can plot it with the model there and then check it here. Oh, okay. So I think you should open your valve in only for one opening, satu putaran. Okay, so that's a simple example of why we do modeling, and also in this case it's not linear regression. Okay. Now, now the regression is actually a statistical method for finding the empirical model that approximate the behavior, the measured data. So we have a lot of measured data, and then here we want to make a regression that can fit those data. Okay, if the equation of a formula of the mathematical model is known or determined temporarily for trial and error, the regression aims to estimate the parameter of the model. Okay, for example, another example is this one. This is the y is the variables, and then another different parameter, and this is the result, yeah, from the phenomena. Okay, and in here it is estimated that this is the model. Okay, so that means if you check this, for example, in this one here, this point, around this point, we have very close to the model. So the model can predict this data. But however, in this one here, this is the model and this is the data. So this one is the error, or the difference between the predicted model and also the experimental data. Okay, and what we want is we want to minimize those errors, so we can have an equation, or the regression linear regression equation, that may fit all the data and have a minimize the data. Yeah. Okay, so what is the best value of m, and to approach the versus x versus data? So here it is a linear equation. So this is a y. Y is remember, this is a linear equation. Y equal to mx plus c. Okay, so okay, so this is a campur-campur, yeah, between English and Indonesian. That's fine. Let me explain one bit. Okay, so this is also another example. Yeah, this is a fitted line plot. So we have a number of experimental data, which is denoted with those points. Yeah, and then they made the fitted line. Okay, so this is the graphical illustration of the method of least square with a fitted line plot for y equal to 5.77 plus 2.591x. So this is the line. Okay, so so this one, y, this is y fitted, so y equal to 577 plus 2.591x. Yeah, so this is called beta 1. Sorry, beta 0. Okay, so this is the parameter, it's called beta 0. Okay, the second one here, the coefficient of the x is called the beta 1x. Okay, and plus, because we will have some errors, yeah, between the measured value and also the fitted value. This is called the error, or epsilon. Okay, so here it is called y equals to beta 0 plus beta 1x plus this is if it is linear or first order. Okay, we also can model the, if you think it looks like second order or kuadrat ya pangkat 2, it also can it's also we also can want to write it as this one. So this is the beta 0 is the intercept, yeah. Here is the beta 1 is for x, yeah, and then beta xx beta 1 1 is for x order of 2 with epsilon. So this is for quadratic or second order. Okay, so this is called linear model. So basically the x is linear. Yeah, this is the first order, and then this one is the quadratic or the second order. Okay, another one, if we also have the nonlinear equation, where in nonlinear equation we have the coefficient x on both on the denominator and also on the numerator and also denominator. Okay, so both of them we have the nonlinear parameters here. Okay, and maybe if we can plot it here, it is not linear right there. Okay, so now the problem is how to predict this one, yeah, the number, how to predict beta 0 and how to predict the beta 1 for the linear regression. Okay, in the past, before Excel is not here, yeah, there's no calculator, yeah, the advanced calculator canggih, or there is no this one, the Excel, yeah, Excel's everywhere. Now you also doing everything online with your own laptop, so you can access Excel very easy, yeah. Before pandemic, students doesn't need to bring laptop to campus, so they have those calculator, the advanced calculator that can also make regression with the calculator. And before that, we have to do this manually. Yeah, we have to do this manually with called the least square method. I'm gonna explain this one in a minute. Okay, so the statistical data evaluation, pengolahan data statistik, is actually we want to find those parameters, this beta 0 and also the beta 1x, yeah, the beta 1. Okay, we also can predict the best or the optimum BI, which is B0 and B1, and then the regression is called this Y with the hat in here, ya, dengan topi with the hat. So y equal to b0 plus b1 beta 1x. So this is the predicted value. Okay, so if we want to find the regression to predict something from the measurement that hasn't happened, this one with the y top here is called predicted value. Okay, so for example, we want to find up to this area around here. Okay, it hasn't been measured, but we want to predict what is the value around this area. Okay, so it's called predicted value. But if you want to compare the actual y and let me check the colors here. Okay, the actual y with also based on the measurement here is called the fitted value. Okay, for example, okay, so this is my measurement around this area, but I want to change it. I want to compare it with the fitted value. So this is the y of the fitted value. Okay, let me explain a few more slides, and then let us pause and then ask for some questions. Okay, right. So the method to get the regression with good parameters or the optimum parameters is called the least square method. Yeah, least means paling sedikit, ya, the very least. Square mean dikuadratkan. Okay, And then so we make the difference in a quadratic, in a square. We make it, kita buat jadi kuadrat, and then we want to make that as the least, yang paling sedikit. Okay, so we started with the deviation or the error. Okay, so first just I have to have a very quick sketch there. Okay, if we have this one, this is the y, for example, this is y equal to b0, beta 0 plus beta 1 x, and this is, for example, is the data. Okay, so this one there, that is the error. Yeah, this one is the error. This one is the error. This one is the error. Okay, if we have, for example, 10 set of data, the experimental data, so then we have 10 error, yeah, with the parameter that we want. Okay, so the error is actually the y, the number, this is the value of y, yeah. See, this is the value of y. So y, this is minus with the model. So this is the model, which is the model is beta 0 plus beta 1 x. So this one. Okay, so we want to make this as a square, and we want to add all of them, sum of square least square method. So we want to make it as a square. We sum of all of them, and then we make it square. Okay. So all the error, why the error should be squared? Because sometimes the error can be negative, sometimes the error can be positive. So if we added all of them, so maybe the positive one can cancel out the negative one. So what we want is we want to just let's make it square, and then we add it. Okay, so this one. So we make it square and we add it there. So this is the sum of deviation square. Okay, we call it L. Okay, we know this one is from experimental data, so we know it. Okay, kita tahu data ini, ya, karena dari eksperimen, dari poin-poin tadi. Okay, so we also know, yeah. So see the experimental data is those blue dots. Yeah, so you measure that, so you got the data. You also know the X from experimental data, because, okay, let's check, for example, if the X here, then this is the resulted Y. If the input here, this is the output. Okay, what we want to find is the beta 0 and also the beta 1. Okay, how to get that is we want to if we have a function, and if we want to find the optimum one, what we need to do is we have to derive it. Diturunkan. Okay, so we have two types, yeah, two steps to derive it. First, derive it with respect to beta 0. Kita turunkan ke terhadap beta 0 ini, ya. And the second one, we derive it to beta 1. Kita turunkan terhadap beta 1. Okay. So if we want to derive it with the beta 0, you can go back to your calculus and then check it the method. Yeah, if you forgot that one, check with calculus how to get that. So if we have a function and we want to derive it with partially to the beta 0, you want to make the beta 1 as the constant, and this one is also the constant. Okay, so the variables is only beta 0, and then so this is a square root, a square. So we derive the square into a 2. Yeah, so 2 of the function, and then for the power or the order of 1, and then you derive the beta 0, and then you get minus 1. Okay, equal to 0. So this is the derivation with respect to beta 0. The second one, the derivation beta, with respect to beta 1, we have to make the beta 0 as the constant, and while the beta 1 as the variables. So here the variables is beta 1, and then this is the derivation. Okay, you may want to check the method, is it right or not? If you want to check, and then check with the calculus there. And from here, from the sigma here, you want to rearrange those the equation there. Then you will find this equal to n beta 0 plus beta 1 sigma x1, and then sigma y, sigma x, and so on. So, and this is called the system persamaan normal. Yeah? So this is called the summation to find the beta 0 and beta 1. Up to this side, it's actually but it's actually pretty easy actually, because here we have beta 1, and we have beta 0 and beta 1, and then this is a number, right? Angka, yeah, this is a number, a number. This is also a number. This is number, and this is number. So you will have two linear equation, and also two variables. Yeah, so there's the first equation, this is the second equation, and the variable is beta 0 and beta 1 that you don't know and you want to know. Okay, so then if you remember in high school, if you have two linear equation, you have two variables, you can get the value of those variables. So you can get the beta 0 and the beta 1. So in the past, that's how the students or our Bapak-bapak Ibu dosen, ya, try to do that to find the appropriate linear equation. Okay, so and then if we so basically we also find that if just to rewrite again, so this is the normal equation that we derived before, and then we also introduce the following sum square. Okay, this is SS, or a sum of square x. Yeah, sum of square x is defined as the sigma of the delta between x model and the x of the data minus x of the average. Okay, which is this one. And then the second one is the summation of y, the sum of square of y, which is y of the data minus y of the average, and then they also can get it. So this is the number n is how much the experimental data that you have. Y dash here is the average, and this is also the sum of square of y xy. So this is how you got it with the formula. You can get the formula. You can have a book. You can put it in a book, or easily in the exam. You're not ought to remember it. So we may want to put the formula on the exam, yeah, by in the exam sheet. So from this one here, the to get the beta 0 and beta 1 here, we also can get, based on some derivation, we also can get the B1 is the sum of square of xy divided by sum of square of x, while the B0 equal to y average minus B1 x average, and then we can get that one there. Okay, so even you have Excel now, you can just click one or two with the Excel, but the method is very important for you to check, yeah, and then this also can be applicable for high order equation, pangkat 2, pangkat 3, pangkat 4. The method is also the same. It's called the least square method, which we find the error first, and then we square it, and then we make sum, ditambahkan, dijumlahkan, and then we derive it to the respect of those variables, so we can get the minimum value. Okay, so this is the an example is the calibration curve. Yeah, the relationship between the instrument reading, for example, and the input. For example, the calibration of spectrophotometer, including absorbance and analyte, the concentration, the measurement uncertainty should be included, and the behavior of the instrument is not necessarily simply linear. Okay, so this is, for example, there are 4 data, and each data is they have those uncertainties there, and then we use it with Excel, yeah, there with the trend line, and then this the equation, and then you have the R square. Okay, and this tell you the R square later on will tell you the quality of the regression result. Okay, I think this is the last of the end show. So if you want, do you have any questions? 1 or 2 questions? No? Okay. If not, then I'll just gonna give a very simple example based on my my kids' health. Yeah. So I'll show you this one. So a few weeks ago, exactly two weeks ago, my first son has a looks like had a DB, yeah, demam berdarah. Okay, so then I plotted the thrombocytes. So they have to check darah, yeah, to check the blood test, and then to check with okay. So that is an S1 or the dengue fever is positive. So we check those every day. Okay, this one is still at home. Okay, so this one is still at home. Okay, so we live for a few still care under home care. Okay, and then this one is 139. The minimum value is 150, 150. Okay, so this is bad. So we went to the hospital, to Boromir Hospital, and then my son is hospitalized. Okay, because they have to take care of the electrolyte and infuse, yeah, and with drip and everything. Okay. So the first day and the second day, of course, it's a lot of fever and so on. Okay, and then we check again. Okay, so the 5th day is 5. Okay, so the 5th day. So this I'm gonna put this is day 1 and day 2. The 6th day. The 6th day is still dropping. Okay. So I was of course. We have to think, yeah, at that time, because in this case the fever is gone, but it is called like very, very critical with the demam berdarah, yeah, with the dengue fever. And then in the 7.5 days, because they took it in the morning and also in the evening, it becomes 50. So what I would do is to make I plot that one there. You can check with the Excel there, and then put with the scatter. Oh, okay. So here, based on here, okay. So this is the trend, right? Okay. So this is the trend. So what do you think? Is it so from here, from those behavior? Oh, I can see. Okay, from here is the trend is just decreasing, but then after day 7, there's something good happening. Yeah, so and then it's increasing. So if this one here, should I make it a linear trend line, a linear one, or a square one? What do you think? How should I make the model? Is it linear, garis lurus, or it should be like a quadratic or the second order? What do you think? Anyone? Because here, if you click, if you have right click, you can add trend line. Yeah. Here in the add trend line, you can click linear. If in the linear, it would be looks like this. Okay, but you know what? I can see something good happening here because it's increasing. Okay, so I can use for example, the polynomial, and in the second order. Okay, and then in the second order, it looks like it had a better fit, yeah, compared to the compared to the better one. So it will getting better, not getting worse, for example. Okay, so I'm gonna put manual there, and then this model tell me that okay, my son will be getting better with time. Okay, because they have passed those the critical value there. Okay. And then I also click the equation there, yeah, and also click the R square. The R square will tell you how much the data fits the model, yeah, how good the model fit the data. If it is more than 0.9, lebih besar dari 0,9, usually the data fitting is good. Okay, so I would say okay, so looks like my son's getting better, and then he can be discharged in a few days. Okay, and then so that's what it is. I would predict it will increase, and then here based on that one there, yeah, I just want to add some more now based on the complete data set that I have. So after this one there, they it's still a little bit similar there, but it's increasing in the day 9 there. Okay, so it is increasing. Oh, okay, so then good, everything's good, and then my son can come home. Okay, so that's an example. Okay, that is just that is to tell you that if you want to, you can have a judgment. Well, of course, you don't need to write this one. Of course, yeah, of course, the doctor and the nurse know. Okay, of course, you can go home. For example, of course, your son will be getting better. But this is just a simple example that with the model you can predict something. Right. Okay. Quite interesting. Of course, you don't want that one, yeah. You don't want to have the mamba data, of course. Right. Now let's go back to the second our discussion, the second one. So how good or how bad is the model? For example, how good or how do you know that you have a good experimental data or you have a bad experimental data, or it doesn't reflect your the phenomena? Yeah, the model doesn't reflect the phenomena. Okay, so the closeness of the regression to the curve to the measurement data points actually reflects the quality of the regression results. Okay, so sometimes if you and this can be expressed by the R square. So the R square that I just clicked before is very easy, like in 2-3 seconds with the Excel. It's actually based on those this calculation. We have to find the Y model minus Y average divided by Y experimental data minus Y average, yeah, and in the difference is in a square and in a sum. So this is called R square. It's called the coefficient of determination. But with the Excel, you can have just 1-2 seconds, very easy, or even in other softwares called Minitab. But however, sometimes if we make a higher order, for example, dibuat jadi pangkat 2 atau pangkat 3, ya, sometimes the R square can be higher because it is make it fit, yeah. For example, you have the second one like that. Okay. For example, this is the linear R square. Or maybe you want to make, okay, look, the same data. How if we make it, for example, second order, jadi lebih bengkok misalnya. For example, ax squared plus bx plus c. Usually, this s square can be higher, yeah, compared to this one. Or for example, oh, I want to make, we call it more like overfitted. Okay, I will make this model Bu Winny because it looks nice and then it can fit all the data. Of course, the R square maybe can 1, yeah, but it just doesn't reflect the phenomena, yeah. So if you increase maybe this can be a x pangkat the order of 5, for example, yeah, it can be like that. The x, for example, yeah, but it doesn't reflect the quality, yeah. So what you can do is you can make the error adjusted, which calculates whether the model is too high ordered. Yeah, this one is high ordered. You don't want that one. You don't want to have a sophisticated model when you can just make a linear and simple model. Okay, so the R adjusted calculates where the model is too high ordered by writing 1 minus the sum square of error minus n minus k. K is the order, that one there. Oops, there, and then divide by sum of square of total there, n minus 1. So using this formula, you can check, for example, this one is r square, this is the r square, 0.7. Of course, it doesn't have a very good fit like 0.9, but that's fine. But still, the trend is linear. You can see with your eyes. Lihat dengan mata Anda, trennya apa? Turun, naik, linear. If I look at it with my eyes, this is look like a linear, right? So, but with some another outliers data over here, yeah, and this one here, and here the adjusted is just slightly lower, 0.728. So if it is quite similar but slightly lower, it's fine. Okay, but if you, for example, you want to find you make it, for example, with the order of 5 or order of 6, and you have r squared 0.9, and then you have r adjusted only, for example, 0.6, then your model is too high ordered. Okay, right. This is also the this interpretation of correlation. Yeah, this is 0.9. This is called the how the quality of those interpretation coefficient. This is 0.9 looks like. Okay, this is the sum of square residual, and this is the sum of square of error around here. Okay, there's the number as usual. This one is 0.75, for example, the data where the sum of square total error is based from the residual and also from error. This one, yeah, the error is 0, sorry, because it doesn't have any trend at all. Doesn't have any trend at all. So this is the error of error. And this is 1, which is based on the total is based on the residual there, and this one is 0.5. Okay, so you can see the quality interpretation of correlation coefficients from the good one and also from a very bad one here. So basically, more than 0.9 is a quite good correlation. And also here we have a confidence intervals and also prediction intervals. So the confidence interval shows you the interval containing the truth of y means given of value of x. You also can learn, you have learned the confidence interval before, but if you want to apply it in here, so if you have this one is those the red one is the experimental data. Yeah, the glucose, for example, the hemoglobin and the blood glucose level. This is the experimental data there, and this is the model, the black one. Okay, so the white one, the blue and the green one is called the confidence level. Okay, this is the confidence level. And this one, while the larger one is called PI or prediction level, will state the interval containing y value will appear if we take measurement at a certain x. So this is the area, yeah, of the prediction. Okay, so the confidence interval for regression parameters can be assessed by the the quality of regression can be assessed from the confidence interval of regression parameters. It can be, for example, confidence interval with for example, confidence level of 1 minus alpha. This one, yeah, confidence level with 1 minus alpha for beta 1, for example, this one. And then this is the standard errors, and then you can get the value looks like this one. Okay, so still like, because the model is also a prediction, right? So, and the prediction, of course, in any prediction we have those interval, confidence interval, and also prediction interval. And then this will tell you about those confidence interval and the prediction interval. Okay, and then just discard this. And then the last one is the regression with care. Okay, so okay, so sometimes we have to, like I said before, we have to see the data first, see the data with our own eyes. So we plot the data. So that's why I always ask the students in the lab or in the chemical engineering lab, yeah, in the lab tech, if you have the data, please plot it first with your hands, with manually, or with your calculator, or even with your laptop there. Plot the data and then see what is the trend of the data. So things should be considered when doing regression is the first, to assume that the residual or the yi and yi top there, the model, yeah, yi and the model is normally distributed and independent with zero mean, constant, and variance. If the assumption is violated, the accuracy of parameters estimation of beta 1, beta I, or the form of regression model chosen is questionable. And it is advised not to plot the measurement data before regression. It is important to ensure the existence of linear correlation and identify the outlier data points and so on. Okay, so this is for example, this one is the measured data strain and then a modulus Young of a polymer. In a bahan, yeah, in a material, or maybe you learn in physics, you have some correlation between modulus. So this is the, for example, this is modulus Young, which is equal to sigma, and this is called strain. Yes, this is strain. This is stress and the strain. But sometimes in polymer, for different E, the strain also will have with also different value. Okay, they okay. So and then they have different. They have and in polymer they have different modulus Young and also a different strain rate. Okay, so and the different strain percentage. So here is the data. They plot the if this is the strain and this is the modulus Young. Okay, and then plot that, and then this one here. So if this is the modulus Young, and then this is gonna be the strain. Okay, so the first one, to check if it is the linear, we check the trend first. Okay, check the trend first from the eyes that we're looking at. Okay, is it linear? Should be like this. Okay, but while or maybe okay, the linear should be, if you're linear, it should be like this. Okay, so in here there's too much gap. Okay, so then so this one is not correct. So I think from our eyes, it is better if we check this one. The area, it looks like that it's gonna like melandai, yeah? Decreasing around here. Okay, this one. A type of graph like this is called the exponential. yeah, or order. So the way to linearize that one is to by using log. Okay, so the second one is we want to usually that's a lot happens in engineering and chemical engineering. We make one of them is or two of them as a log, yeah, as the logarithmic. So makes this as a logarithmic, this one, yeah, make a log, and then well the strain is still the same, and then we check it. Okay, and here we can see the trend looks like more like a linear there. Okay, so this is a linear. Um, then you can get the R square around 0.7. Okay, so the XY diagram graph with the original data showing nonlinearity y, yeah, equal to fx. And then you want to try making y equal to log x diagram, and which result in linearity. Okay, so I think yeah, so this one is also happening. So there would be intercept and multiple regression zone. Sometimes it might be happen. So we can check the data there if around here is linear and the second one is linear. So this also can be linear. Okay. In the matter of intercept, yeah, and also is it should be set and zero, we have to check also the phenomena. Is it should be start with zero or not? If it should be start with zero, then we can make it intercept as the zero. While if in the meaning is there is no meaning of zero in the intercept, then we don't need to put the intercept as the zero. Okay, so so as the conclusion to develop good model, you while we need 2 hours for this, yeah, for regression, because you will find the regression a lot in your chemical engineering lab, in your research, in your work later on, yeah. And then the good and proper regression model can explain as much as data behavior possible with small number of parameters. Okay, this one is called overly simple model will give low R. So this is called underfit. Yeah, but however, the overly complex model or overfit will give high R like this, but it is too much, and then it will lose the physical meaning. Yeah, the physical meaning. Okay, so the risk in modeling is underfitting or overfitting, and an overfitting the model tries to approach much data or too high order. This one we don't want this one, we don't want this one, we want the optimum one. And as you know, the behavior of system, of course, is not always ideal, so it is okay to have a discrepancy of the data like this, as long as we can see the trend, and then we can describe that one. Right. I think that is the one that I can explain to you. Before we stop, any questions? No? Okay, then I think we can have a few few more hour. Okay, a few more hour uh, with check. Please check your EduNext, yes, the self-study. Check your EduNext, and there are also tutorial in Pak Miki's lab there, in Pak Miki tutorial, and then for the tutorial for regression. Especially it's about, let me check there. Um, I would like you to open the, oops, that one there. Yeah, this one, the tutorial, almost half an hour, but please have a look here. Pak Miki give you a number of tips and ideas in the tutorials using Excel. All right. Any questions? Yeah.
Okay, Bu Winnie.
Yes.
I think I can help for another hour, yeah.
Okay, good, Grace. Okay, I really have to go because at 9 o'clock there is international accreditation, Bu Grace, IAB, with technique metallurgy. So I have to check everything before it starts. Okay. I will ask Bu Grace to memandu ya to guide the session. Thank you very much, Bu Grace, and then I hope that can help you to much prepared for the exam next week. Thank you very much. Bye-bye.
Okay. Thank you, Bu Winnie. Okay, everyone, I think we will need a tutorial, yeah, for the second exam, the second module exam. So please check with Evan, yeah, I think, yeah. The chief of this class is Evan, is it right?
I don't think so.
Oh, who is the chief of this class?
It's me, ma'am.
Okay, Azra. Okay, please discuss with Azra when you have maybe about 1.5 hour, yeah, 1.5 hour for the tutorial, or at most 2 hours, yeah, for the tutorial for the exam preparation. Please check with that. And now I think first any question, or if not, then you can go watching the videos from tutorial, yeah, because from there you will get the idea how Excel work, yeah. And later on I will also show you actually behind the Excel what is going on, okay? Or do you prefer me showing the videos of Pamiki? Please give me a response. We can stop the recording, yeah?